Excellent. Thank you, Andre. And I'd like to thank all the organizers for the invitation to come here, and thank you all for lasting through the day to attend. I'm going to talk a bit about kind of an arc that kind of goes over my entire career and meshes different aspects of what I do together. Now, in my other life, I'm a gravitational physicist, so being in Cambridge is like being on hallowed ground for me. Of course, because Newton here, this is in Trinity College, there's a statue of Newton, so I was very excited to see that. Newton's apple tree, if you go into town, you can see that as well out there. And of course, it wasn't just Newton here, it was also Stephen Hawking. Now this is his gravestone in Westminster Abbey. I snapped this last week in London. I'm going to, although these don't seem to have anything to do with art, I am going to tie them in at the end of the talk. And in fact, it is my interest in gravitation and cosmology that actually got me into this artwork world in the first place. So our story begins back in 1998. So I had just started my PhD at the University of Toronto in the physics department, and I was looking for a topic for my thesis. So my advisor and I decided that I would study the statistics of galaxy distributions, formation models, and compare these distributions to actual observational data. Okay, and we were going to do fractal analysis, because that was kind of in vogue at the time in astrophysics and cosmology. Well, along came a colleague of my advisor who is a psychologist, and he was interested in aesthetics. And he heard us talking about this fractal structure analysis, and so he said, this is him, is Gerald Kupchak, he said, you know, hey, when I look at Jackson Pollock paintings, I feel it. It does something to me. There's a structure in those images. You go look at those images and figure out what it is. And so we brought him in on my thesis committee, and he's actually the keynote speaker this year at the International Association of Empirical Aesthetics Congress. I just learned, so that kind of ties into the president as well. And so we went to my PhD proposal talk and talked about this, okay? And let me come back to this. And they listened, and I said, okay, well, you know, the galaxy stuff, sure, yeah, do that. This artwork stuff, that's not physics. You can't do that in a PhD for physics, so go rethink it. And so I went away. The very next day, this article appears in Physics Today. And this is, of course, the pioneering article by Richard Taylor and his collaborators that showed that, well, can science be used to further understand art? And so they said, right, here we analyze Pollock's patterns and show that they are fractal. In other words, they display the fingerprint of nature. And again, right? So this was October 99, literally the day after I was told it wasn't physics. So I went back, I win, right? So I got, this was the beginning of my journey. And as we went into this journey, this quote from Pollock came up as well. It says, any attempt to say something about art, to attempt any explanation of the inexplicable, could only destroy it. So we said, sounds good to me. So Pollock wasn't there to stop us, so we walked forward. And we did a fractal analysis. Now, we've been talking a lot about fractals, so I probably don't need to say too much about this. But what are the characteristics? Well, we just had an argument about what a fractal is. But what are the characteristics? So it's an object whose parts somehow resemble a whole. Right? It's defined by self-similarity, scale invariance, recursivity, an infinitely nested structure. And most importantly, it's characterized by this non-integer dimension that we call the fractal dimension. Okay? And mathematically, I can write that relationship as the following expression. So on the left side here is some kind of characteristic that is a function of scale, d. Right? The scale, of course, is the ruler length at which we're measuring things. And df is the fractal dimension. Now, let's talk about what a fractal is by talking about what a fractal isn't. So if we look at Euclidean geometry, we have various shapes that are defined by the dimensionality of their, that characterizes them, their topological dimension, we'll say. So a point has 0 dimension. A circle has dimension 1, right? It's a linear object. A disk has dimension 2 because it's an aerial thing. And lastly, a sphere has dimension 3. right? And that, now we can still use the fractal dimension characteristic equation because we know that the circumference of a circle is 2 pi r to the 1, the area is pi r squared, right? And the sphere is 4/3 pi r cubed. So in each case, right, there's the fractal dimension corresponds to the thing that defines the characteristic of the shape, and that matches that thing. Okay. But again, most people know this. And so we can also think of fractals as something that are a little less than or a little more than Euclidean. Okay. And that's sort of an esoteric definition. So what are some of the classic fractals, right, are things like the Koch snowflake has a dimension of 1.26, so it's a bit more than linear. The Sierpinski triangle has a fractal of 1.58, so it's a bit less than an aerial object. Then, of course, the famous Mandelbrot set, right, actually has a fractal dimension that pushes the limits of up to about 2, so it's sort of an area-filling object. And so on and so forth. So these are our classic ideas. And we could talk about construction of fractals as well, right? So again, the idea of recursivity or repetitive construction is at the heart of a fractal. So I start with a triangle, and if I cut one triangle out of the middle, I've got 3 left at 1/2 the scale. And then I'm going to repeat that construction process in those guys, right? And if I keep repeating it in the gray triangles, then I get that, and blah, 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 and it goes down on and on. And so what I have is I have a certain number of new triangles appearing at the scale factor at which I'm defining it as, right? So obviously, the red triangle, the green triangle are the original triangles themselves. And so we can define that fractal dimension to be the log of the number of copies over the log of the inverse scale, as Andre talked about the other day, and that gives us our fractal dimension. And I think this is sort of, the Sierpinski triangle is kind of interesting because, again, there's a connection to Cambridge. If you go out the front door right here and turn right before you get to the sidewalk, you'll find this about 20 meters away. This is the Sierpinski tree. Okay, it's an interesting little structure out there, a little sculpture, and it again incorporates this idea that natural objects have a fractality to them as well. Trees, for example, which will be important a bit later. So how do we measure a fractal dimension of a set that isn't a mathematically exact thing? If I don't know how many new copies appear as I decrease the scale. Okay, so I'm not going to belabor this a lot. I'll just say that there are 2 basic ways to do it. There's a top-down method where you start big and go small, and you see how fast can I replicate or kind of, shrink wrap my analysis onto the actual shape of the fractal. Okay, as I decrease a scale resolution, and this is the box counting method or the perimeter length method, and that's basically what I'm going to be talking about. Just briefly as to how we do the analysis. And just for completeness, there are other ways as well. The bottom up. You start small and start exploring outwards to see how the structure changes as you increase the scale length instead of decreasing it. And this includes statistical methods such as the endpoint correlation function, mass, radius, or what's called the conditional density. But for the analysis that I have done with my colleagues, and in fact, it's an analysis that carries over to the different things we're going to be studying. We're going to look at the box counting method. So the idea is as follows, right? So you have some structure that could be fractal or not, but we ideally hope it is. So what are we going to do? Well, here's the structure contained in a box. So we're going to subdivide this box into smaller boxes of some scale 1 over n, whatever that is. And in this case, I've cut it into boxes of scale 1/6 the side length of the original, and I count the number of boxes that the pattern appears in. Okay, and so there's at 1/6 the scale. There's obviously 36 boxes there, and if you count the occupied ones, there's 32. Okay, and then we're going to cut the scale of those boxes again. Okay, now we have 81 boxes because we're down to 1/9 the scale. and there are no 62 occupied. So what we can see is that as we decrease the size of the boxes, there's more empty boxes that are appearing as the scale size goes down. So if I cut it again, right, to 1/15, I've got 225 boxes. Now only 79 of them are occupied. And I can keep doing this down to whatever scale I wish to do it. And ultimately what I'm going to do is I'm going to take those data points of the number of filled boxes, plot the log of them versus the log of whatever the scale. This should hopefully give me a linear relationship, which I identify with the fractal dimension. All right. So that's the basics, and that's kind of the analysis method that we're going to use. And like I said, it's going to carry over to other things that go deeper into fractality and also that go beyond fractality. So let's get back to our story. So Taylor publishes this paper on fractal dimensions and validates the work that I'm doing. So I reach out to him, contact him. So what was done originally? Okay, well the idea is the following. So we all recognize Pollock paintings now. They're this, abstract drip and spray. And what we do is we filter out a particular color. Okay, so we have an algorithm to do that. I can go into details if needed. But basically, we pick the black pattern, let's say, and filter that out and remove everything else. So this provides the pattern that we're now going to do a box counting on, and it will give us the fractal dimension. And we need a consistent set of data to do this, so we can take a second Pollock, in this case Blue Poles, one of his famous ones. I think this is one of the ones that's worth the most money. So if we figure out how to do this, right, we're in the business. And then we filter out the black pattern again, right? And you can do this with different colors as well and study those. So you get a whole set of data about what the fractal dimensions of the different patterns are, depending on their color, and so forth. So this was basically what Taylor did in Taylor and his colleagues did in their original study, and gave me something to reproduce in my studies. And this is from Taylor's paper, but essentially what he found was that there's a consistency in fractals, or in Pollock's paintings, vis-a-vis the fractal dimension. Okay? And in fact, what he noticed is something interesting. He noticed there's a bifractal characteristic to the patterns. That at the large scales, the slope is steeper than it is at the smaller scales. And Taylor and his colleagues attributed that to the fact that there are two separate motions that create the larger scales, which are like, the hopping around that he would do, and I'm just assuming he did that, and then the smaller scale motions of his hand or his wrist or his fingers. Okay, and that's the fingers and wrists down here, and this is the body movements. Okay. And he found this was pretty consistent for Pollock, and we did as well. We reproduced that. But we couldn't just redo Taylor's analysis and end it at that. Okay, so we had to dig a bit deeper, and this is where the collaboration with the psychologists came in. Okay, why would we paint fractals? If Pollock is painting fractals, whether consciously or subconsciously, why do it? What makes that interesting? Okay. So what would motivate an artist to do this? And there's a wealth of information in the literature, in the aesthetics world, about what makes things interesting to look at. Okay? For example, back in the 1800s, Fechner proposed the principle of the aesthetic middle, said people like to look kind of like, it's like the three bears. People don't like too complex, they don't like too simple, they like moderate. And again, that's echoed in here, right? Aesthetics requires a balance between order and complexity. More recently, Berlin at the University of Toronto proposed that there's a biological aspect, a physiological aspect to aesthetic interest. Okay? So he said every behavior, including aesthetic activity, must be related to biological structures. So our perception of the painting is triggering something in the brain. And this is something that was discussed earlier, is the idea that there are centers in the brain that are attuned to picking out certain patterns. And so that ushers in the idea of what we call fractal aesthetics. So fractal aesthetics is a synthesis of a variety of different sciences, social sciences, hard sciences, psychology, humanities, biology, mathematics, physics. And it's all about how the pattern may be itself a fractal, but it's moreover how we perceive the fractal and how it gets processed by our brains that triggers the response. Okay. And so this is kind of the road we started taking instead. And to one up what Taylor had done, we said, okay, well, they did a fractal analysis, but there's much more than fractals in the world. There are things called multifractals. And what a multifractal is a set of, it's a family of infinite number of dimensions that characterize a multi-scaled image that can't be characterized by just a single dimension. Okay, it's defined by a parameter q, so I have going from that should be d of minus infinity up to d of infinity. Okay, and these three guys in the center, D0 is the usual fractal dimension. Okay. D1 is called the Shannon information dimension. D2 is called the correlation dimension. Those are standard things in statistics. But the upshot of what the multifractal spectrum tells you is it gives you a sense of how the densities of the patterns vary across the set that you're interested in studying. So again, it's that, so I won't do math, okay, I promise, even though we're all math people here. I tell my students when I teach an on-science course that there's some math in here, but it's fun math. Right? Okay, so anyway, so here's how you calculate the multifractal dimensions. They're essentially just increasing moments of the variance of the distribution. So. And that's it. So I'm going to leave it at that. I can fill you in on this afterwards if needs be. Okay. But again, the multifractal dimension is predicated on this parameter q. Okay, so what does q tell us? It's a magnifying glass that as we turn it up, okay, it's going to focus in more on the clustering details of the image. Okay, and q goes up to 11. Oh, all right, someone got it. All right. So anyway, so Q goes up to infinity and it shows the strongest clustering sets. You can also dial it to negative infinity, which shows the least dense regions. And just to give you a sense of how this works, here's 4 different point sets that we can analyze. This was, again, from my thesis. This is a cosmological model. It's called the Swiss cheese model. This is an ordered lattice, square lattice of points. A random distribution of points, and what I call a pseudo-random star set. It's kind of like a fuzzy axis. You can see it's got linear shape to it. The multifractal spectrum of the Swiss cheese model, that's it here. Okay, these are little vacuum bubbles, it doesn't matter. They're all nested together. It's like something you would doodle if you're listening to a really boring talk. And you can see the spectrum goes from the fractal dimension of about 2.4 to the d infinity of 2. Okay. And what this means is that these bubbles cluster preferentially on the surfaces of other bubbles, right? D equals 2 is an area. The random distribution is basically between 3 and 2.85. That's probably numerical. It's ideally 3. The ordered lattice is pretty volumetric in its distribution as well. And the star set is the most interesting because at the fractal level, it's a random set of dimension 3. But very quickly, the multifractal analysis is able to pick out that its most dense clustering is linear. Right? And again, you can see it in there, right? It's just a little cross shape. So we carried out. So we analyzed the multifractal structure of Pollock's paintings. We analyzed the multifractal structure of other artists as well. As was mentioned before, it's a Quebec group called Les Automatistes. So this is Au Château d'Argonne by Marcel Barbeau. And again, here's the filter of the black paint. Tunut by Marcel Barbeau, another one. We filtered out the black paint. And we also looked at an artist who was a colleague of the psychologist. He played a strong role in this, named Jonas Mureika, and he had an art system he called artonomy, where the art was created by mathematically precise algorithms, and we analyzed those as well. Yeah, it's just as a control group. And when you look at the multifractal spectrum of each of them, there's 4 Pollocks here, 4 automatists. I guess there's no Avital in here. Okay, so it's kind of a mess. But you see the fractal dimension, again, is kind of consistently around between 1.6 and 1.8. And the d equals infinity fractal dimension tends to be lower, okay, around 1.6 to 1.5. All right, so and that's what I just said, so I'll skip over that. So that was interesting. It showed us that there was a consistency between the automatists and Pollock. So is there a way to kind of differentiate them some more? Okay, well, one of the things I did in the years that followed is I said, well, again, back to this idea that maybe the people looking at the painting have something to do with what they're seeing and not just the pattern on the paint. So I filtered, instead of using an RGB color scheme to filter out the patterns, I used what's called the LAB system, which is a perceptually uniform system, because in RGB, the distance this far in the red is not perceptually the same as the distance that far in the yellow, okay? Or, sorry, there's no yellow in there, in the different colors, right? So they're different. And I won't spend a lot of time on this, but the upshot is that the fractal dimension favored the dark blobs between the color sets, but the lighter ones were disproportionately lower in the RGB channel, which meant that there was a richer structure for the lighter colors that was perceived, okay, and not painted on there. And more than, going beyond that, the idea is, right, the paint blobs themselves, it's established those are fractal. So, but the question is that what we see first? Okay, we've heard already today that there are a number of centers in the brain that are attuned to picking out things like luminance gradients, edges, things like that. And in fact, there is some suggestion that aesthetic value and appreciation is triggered by edge detections, okay, hard and soft edge detections, and that's detailed very strongly in this paper here. So what do the luminance edges of these paintings look like? Okay. Well, here's a Pollock, right? The luminance edges are how the colors overlap and contrast, which creates a new structure, okay? And that's that structure. Okay. So this is what those cells in our brain that detect edges are seeing. Right? Blue poles, blue pole edge structures. And so if we repeat this analysis with the Pollocks and with the automatists and with the Avital paintings, the multifractal spectrum looks decidedly different. And in fact, it cleanly picks out Pollocks versus automatists versus Avital. Okay? So this suggests that an attuned person can look at the two paintings and say, this is a Pollock, that's not, because this will sound weird, I feel it. I feel this is a Pollock because my brain is processing it in that way. So we found that was interesting. And what we're going to come back to is the difference between the fractal dimension and the d equals infinity dimension tells us something even more interesting. It's called the multifractal depth. So that was great, right? Okay. And it brings to front the idea that aesthetics and aesthetic appreciation, an aesthetic response, or response to an aesthetic stimulus, is somehow contained in information transfer. Okay? Because the information that is encoded on the canvas is being fed into our brains, right? We are perceiving what's on there, and then our visual cortex, wherever it is, I guess back here, is processing this according to what it sees in terms of the edges, in terms of the blobs, or whatever. And so there's a biological response. So there's physical paint, perception, cognitive, physiological response. Okay? And so the upshot is Pollock paints this, and we all see this. Okay? That's possibly what happens. Okay? Again, in the intervening years, my colleague has done a lot of fMRI studies on people observing Pollocks and other abstract art. And he has a lot of stuff to say about this. I won't be able to talk about it here, but I would refer you to those papers by Jerry Kupchik. I have also been collaborating more recently with Richard Taylor, because I've reached out to him right after he published his first paper and said, hey, we're doing this too. And so we've done a number of studies that follow on the heels of the multifractal analysis. And one of them is we showed that if you look closely and do a high resolution multifractal scan of the Pollock and the Automatiste paintings, then in fact you notice something very interesting. The Pollock paintings tend to have a statistically higher mean fractal dimension than the Automatiste paintings. It's subtle, but it's there. And that suggests there's something different about the Pollock paintings from the fractal side than the Automatiste. But if you look at the whole range of that spectrum, you look at the multifractal depth, which we define, right? The difference between the fractal dimension and the D infinity dimension, those are actually the same. Okay? So the depth of the painting, whether it's Pollock or the Automatiste, is identical. And so that intrigued us because it suggests maybe that's some kind of additional piece of data or datum, I suppose, that can be thrown into an analysis of, or an authentication of, is this a real artist that did this, or is it someone else? Okay. And that was detailed in this paper here. This idea of multifractal depth was something interesting, and so we carried it on. And so we organized what was called Drip Fest at the University of Oregon. And what this was, it's a fest, so it was exciting and fun. We pulled in 18 children and 34 adults and basically gave them a stick and some paint and said, go make Pollocks for us, okay? And you see the dollar signs and everything, this is great. So here's the information about what they did. Here's a sample of their paintings. And then what we did is we scanned everything, high resolution scan, and compared the multifractal structure of those paintings with the multifractal structure of a Pollock, number 14, and Ernst Max's Young Man Intrigued by the Flight of a Non-Euclidean Fly. Okay? And I'll show this in a second. I have it here. Okay, here's the Pollock one filtered out for the black paint. Here's the Ernst Max painting.
What year?
Sorry?
Do you know what year?
That was 1942, I believe. 42, yes. Okay. And just a comment about how he painted this. Max essentially used a bucket on a string with a hole in it, right in the paint bucket, and he kind of swung it around. So it's a pendulum kind of swinging around in 2 dimensions. And he's trying to guide that, but it's pulling him along. So it's basically taking away his fine motor control, and God, who knows what else is guiding him to do this, but that was the pattern that it created. Okay. And so we compared that with the children and adults. So here's a sample child painting. Okay, here's a sample adult painting. And if you look at the multifractal spectra of each, the children start at a fractal dimension of about 1.7 and go, well, numerically, 50 is infinite, right? It's big enough for me. It's 1.46. Okay. Likewise, for the adults, 1.93 is the fractal dimension, down to 1.80. So immediately you see, and this was consistent for all the paintings. So immediately you see something interesting. Okay. The multifractal depth for children is almost twice as big as the multifractal depth for adults. Okay? And that says something very interesting. It says the adults are, whether consciously or not, focusing on trying to repeat the pattern down to the finest grain. The children give up, I guess, right? Or they space out and do something else. If they're anything like, oh, I shouldn't say that. This is going to say about my daughter. But anyway, that was an interesting thing. And in fact, so we did a chart here that shows the average fractal dimension for the gray, which is children, the blue, which is adults, and the multifractal depth for each of them, and compared them to the Ernst paintings. And in fact, the children have a fractal dimension that's closer to the Ernst painting than to Pollock, which shows that the children have a lack of balance akin to what was happening to Ernst as this thing was being painted. And likewise, the multifractal depth of Ernst is up here. So that is a very uniform pattern that was painted by that mechanism, okay, compared to the adults. So this suggested that the multifractal depth could say something very interesting about balance, artist balance.
Sorry, can I ask just a very quick question?
Sure.
Were they deliberately trying to imitate Pollock, or were you just telling them to have fun with it?
Yeah, we just said have fun with the pen. Like, so do a drip method, but don't try. Yeah, we didn't. I guess I should say we didn't specifically say go make a Pollock. We said go drip this paint on, and we kind of instructed them with what the general technique of drip was.
But the adults might have been more likely to have seen.
They might have seen. Yeah, they might have heard of Pollock or seen the movie or whatever. So yeah. So it's not a completely controlled situation. Sure. Okay, so then fast forward to now. Within the past couple of years, we've started looking at what's called the lacunarity of these paintings. And what lacunarity is something that could be classified as non-fractal but also non-Euclidean. Okay? And the word itself comes from lacuna, which means lake, okay, or gap. And the idea is that it's an analysis that studies the spacing or the size of voids in a set versus the clustering. Okay? And what can lacunarity tell us? Well, it tells us a bunch of interesting things. It can tell us some multi-scale clustering properties that aren't apparent in a fractal analysis. Okay? And it can actually be applied to non-fractal sets as well. Okay? Everything has a lacunarity. It just depends on how big things are spaced out. Okay. And again, fun math. All right. So the box counting method is used again. You basically calculate density of points, etc. And the lacunarity, just kind of TLDR here, the lacunarity is the ratio of the variance to the average of the distribution of the points in the set. Okay. And it's a function of scale, so we can get some plots on that. And what did we find? So this is a teaser for a paper that we are currently in the final stages of getting out to for review. What did we find? So here are the four control paintings. Right, here's a child painting. Here's an adult painting. Here's the Pollock painting. Here's the Ernst painting. The first column of plots is the fractal dimension. The second column is the lacunarity. Okay, the upshot of our results are that the children's paintings are characterized by smaller fractal dimensions, but larger lacunarity. And you can see that because they're like very gappy, right? There's not a lot of pattern or structure there. So they're very lacunar. The adults are not. They're obviously it's very, very, very busy. Okay, so they show a smaller lacunarity than Pollock and Ernst. But that's the thing, right? Smaller than Pollock and Ernst, so which is different than children. So this suggests that Pollock and Ernst are doing something that neither the adults nor the children are doing. Okay. And again, this suggests that there's something going on here about motor control, balance, training, technique, and there's a number of other. I didn't have a big enough slide. But we also used the control of the D2 dimension, which was the mass dimension, and that provided a third data point to identify a pattern on. This was, again, this is coming out soon. I hope within the next 2 months or so, we will have it ready to go. And so stay tuned for that. Here again is another another pie chart, right, showing the, here's the Ernst, the red arrow, black arrow is Pollock, here's the fractal dimension. So again, the Ernst, the children are clustering towards the Ernst, where the adults are sort of clustering towards the Pollock. And we see the same thing here with what we call the lacunarity depth, okay, which is the difference in the lacunarity from the largest scale to the smallest scale. And so that kind of completes the, well, I guess it brings the arc up to the present, okay, in terms of how this has impacted my career and how it's been a lot of fun to study. So in the time I have left, which I believe is about 4 minutes, I'm going to give you some parting cosmic thoughts, because I'm a cosmologist. So again, my other hat is studying black holes and gravitation, okay, and quantum gravity, and that doesn't seem to have anything to do with art. However, hear me out. Okay, the notion of fractality, believe it or not, is very prevalent in gravitation. Okay, and in fact, there's a slew of what are called quantum gravity theories out there that try to explain gravity as a quantum phenomena, the same way we have theories that explain electromagnetism as photons and strong and weak force, and this is what we call gauge theories. We can't build one of those for gravity, but we have to build another one. So we have all these, all these candidate theories. String, probably most people have heard of string theory. Doesn't work. There's loop quantum gravity, something called causal dynamical triangulations, asymptotic freedom, and so forth. Whatever these things are, what's interesting is most of them point to one common feature that they all predict. They're different theories, but they all predict one common feature of what we should expect to see at the quantum level in terms of gravity, the shortest distance scales, right? That's relevant to the meeting. What do they see? Well, let me ask the following question. What dimension is a sheep? Here's a sheep. What dimension is this sheep?
3.441.
Oh, he's box counting. All right, so yeah, so the sheep, so as far as we know, the sheep is dimension 3, right? Because we're dimension 3, the sheep is as big as us, that makes sense. But if you zoom in on the sheep, on the wool, you'll find this little guy, and he's sitting on the sheep, and the sheep is that green stuff there. What dimension does he think, or she, sorry, what dimension does this mite think the sheep are? 1? Well, probably 2, right? Because he can see that structure there, but there are smaller things still, right? There are smaller bugs. So there's this bug here, and he sees the sheep as this strand of just a single strand of wool, right? So he sees it as 1 dimension. And so this tells us that it depends who is measuring the sheep to tell you what the dimensionality is. Okay? And yes, this sounds crazy because and that's why I really like the other stuff I do. It's possible that this is what is predicted by those other theories, that at the smallest distance scales, gravity will start seeing the universe as 1 dimension of space instead of 3. Okay? This is called dimensional reduction. And that's an interesting thing because, well, it draws into the notion of what's called fractal gravity. Again, here's Newton's tree that I showed you in the center of town out there, right outside the college. Trees are fractal structures, right? So it's no surprise that Newton's laws really should be modified at the smallest scales so that it's not a 1 over r squared law. It's r squared when d equals 3, but the dimension will start dropping at very short distance scales. So you get what's called fractal gravity. Okay? And this isn't something that I'd like to think it was something I came up with. A lot of people have talked about this. Gianni Calcagni has discussed this a lot in terms of dimensional reduction and the like. But it's the idea that the dimension can not go from 3 to 2 to 1, but can go to integer dimensions in between. Okay? But it's limited. D equals 3 at one end, D equals 1 at the smallest. Okay? And so the universe, and of course Newton should have known he was sitting under a fractal when he came up with gravity, right? So he should have done that. Anyway, so the universe itself has a multifractal spectrum of dimensions. And so that brings me to my last slide. Okay. So this has to do with black holes. Black holes are a key to understanding quantum gravity because, well, again, bringing it back to Cambridge, it was Hawking in the 1970s who showed us that black holes could evaporate, okay? And on his gravestone in Westminster Abbey is the equation for Hawking radiation, okay? It says this, the Hawking radiation is this value here, and there's a lot of number or stuff in here, but the important thing is m. M is the mass of the black hole, and the temperature goes as 1 over the mass. So what this means is the following. When the mass goes to 0, the black hole evaporates down, the temperature goes infinite. And that means I get infinite energy from nothing. So more ways to make money, right? This infinite energy from nothing. But it's a problem. You can't get infinite energy from nothing. If the number of spatial dimensions is 1, however, you can show the temperature goes smoothly as m, and everything's happy. Okay? And so that means if the universe has a multifractal dimension or multifractal depth of 2, quantum gravity works, and everybody's happy, and the universe is great. And so that means the universe must be a work of art constructed with childlike simplicity. And on that note, thank you. The art papers are available at my website for download. All my other stuff is as well.
Okay, David.
I remember when you presented this in my conference in 2010, and I heard you to submit again. We're always looking for good papers.
Sure.
But I will say that the limiting cases at very fine scales are, in fact, altered significantly by the image processing you do. When you take one color and then you take it away, you are introducing lots of missing portions,
Okay.
especially when you do lots of colors. So I have a student at Stanford who did a really great project on taking Pollocks and then finding which is the top layer through statistical methods, deleting it, and then in-painting so that we get the paint beneath, then doing it again.
That's
doing
true.
it again. And so each of these, I'm sure, will change your numbers. And just for the art scholars around here, the reason we're doing this is we want to see Pollocks develop. We want, as a process, as versus time.
Right.
What did he see when he then chose the green?
Right.
And how did it go? So it'll fix, or it'll certainly alter your curves.
Yeah, that's great. I'd like to hear more. Yeah.
Paul.
It's very interesting. In my community, we have seen, I think, slightly different names for things. So the DQ I'd call a generalized dimension.
Okay.
A multifractal, I'd call that when you have the spatial structure of the dimensions changing over space. And I wondered whether that idea might be useful here in terms, again, you're thinking about ranges of measuring different things.
Mm-hmm.
If the spatial, local fractal dimensions are changing,
Mm-hmm.
again, that's giving you sort of a sense of how much the structures are changing within themselves locally.
Okay.
There's not a uniform single number. And there the spectrum is, if you like, probability of finding a certain dimension spatially.
Okay. So will that be tying into what Elsa Maria was doing in terms
I'm
of?
not sure because I was away.
Okay, so yeah, because
I don't think so.
no. Okay. Okay. Yeah, maybe. I mean, I had heard the generalized dimension being called in terms of the multifractal, but yeah, I don't know the answer to that, but that would be interesting.
Just to add, on Friday I'll be talking a bit about some of the how to approach minimalist pictures like this in terms of length scales.
Okay.
Gregor?
Yeah, just a very basic, simple question. You showed that you used the Matisse, the Pollocks and so on, but you only used 4 of the paintings from each group. Did you ever think about building a classifier to get another painting and let the algorithm classify that's a Pollock, That's Untitled, that's a less organized.
Right, we actually use more, we only published 4, but so
Okay.
my thesis has a lot more in them, yeah, so
Yeah.
we were just kind of publishing a representative set.
Okay.
But yes, I mean, yes to what you asked.
Okay. Thanks, yeah.
The other? If no other, I'm gonna say something, if I may. To follow in a slightly different way on what Paul said. When you take a log-log plot, you flatten the curves. Right? If you have a polynomial, you get a straight line and so on. It turns out, if you look through literature, when you look at these log-log plots, that in fact they're very often only approximately linear. And we just did a study, like your paper, it's being reviewed right now, so I hope it will come up. In many structures, synthetic and otherwise, the fractal index, I call it, that is to say the slope of the log-log curve varies not with position within the spatially, but varies with scale. And
That's just periodic with the logarithm of the.
not periodic. For very large scales, it has to go to 2 for a flat thing. So all of these curves, if you extend scales, will go to 2. But even we've analyzed also, if I may say, Pollock, and if you look very carefully, it turns out the slope varies. So when you fit, what you're doing, you're fitting straight lines. I encourage you to get more points so you can take a derivative and look at the varying slope. And you will see that there is a wealth of information in your own data that you haven't looked at.
All right, challenge accepted.
Are there any other comments or questions? Elsa Maria.
Thank you. Are you correlated the multifractal dimension with complexity?
We didn't look at that, no. Yeah, I mean it's complexity defined in terms of what kind of parameter, like the Betty numbers, or yeah, we didn't look at the Betty numbers. No, we just kind of stuck to the fractal the multifractal spectrum ideally, right?
And linearity is related to the host, the number of
Yeah,
hosts.
that's right. That's right.
It's similar, no? It's because
It's conceptually similar. It's kind of the inverse of a fractal analysis, right? But and it uses the box counting and the same idea, just gets to a different statistic. Yeah.
Any other comments, David?
Just to say that that's Newton's tree out there as well. You could have gone less.
Oh.
There's another one here.
Oh, there. Okay, so there's multiple.
Just outside there.
Oh, interesting. Okay, well, yes, I'll do that then. See, that's the one on Google out there.
Okay, if there's no other comments or questions, let's thank Jonas.